Hi guys, time for a new video again. This time, of course, it will be something with at least a little high voltage. Yeah, 300 volts. That's not really high voltage. If you see that here, 300 volts. But it's good to play. Well, honestly, I would never ever had bought this device if it wouldn't not been bigclivedotcom channel, where I saw a video where he presented this thing, and not because I'm interested in testing LEDs like that, but I saw when he opened it the insides and I liked it. The only reason that I bought this thing is to tear it down and make a complete reverse engineering with a complete reverse engineered schematic, yeah, and with explanations and data sheets to show data sheets of the more interesting parts, etc. So the first thank you goes to bigclivedotcom for showing me that, and yeah, making me to buy it and play with it. Yeah, he found out when he tested it, he found out there is an additional mode that switches between 318 or 19 volts by shorting the output leads for a amount of time. This is that shows more or less the device that the LED on the output is either the thing is shorted or the LED at the output is a low voltage LED and goes down from the 300 volts to the 19. Anyway, this thing is called HWL300. It's called a Super LED Tester. Yeah, but honestly, when you see what is inside, and I explain you the schematics, you will see that this thing is, for Chinese standards, really a Super LED Tester. Yeah, and they made a lot of thoughts to make this thing as safe as possible. Yeah, let's turn it on. Of course, it takes a while till it ramps up to the 300 volts. The flickering is from the camera. Yeah, here it's better. Anyway, let's test it. Okay, I don't have many LEDs. BigClive has a myriad of LEDs, different ones, and combination of those. This is just from a broken LED lamp, an old LED lamp, but it is okay for testing. There are 1, 2, 3, 4, 5, 6, 7. 7 LEDs. Let's go to test it. First of all, you see that there is a soft start. This will be explained in this schematic later. And we have here 19 point something volts. This is awful here. I don't know how to do it. Found it. Just get the light away. Now I'm not seeing anything. Anyway, let's do it again. 19 volts. Then if we do it like that to test only one of the LEDs, does it work? Let's take this one. Yeah. 2.3 volts. It regulates down to 2.3 volts. That works good, yeah? So, normally what I saw is that if you keep it longer, it should go to the 50 milliamps. That was, wow, that's bright. That's 50 milliamps. That's 50 milliamps. Let's go back. These are the 20 milliamps. Let's wait again. I didn't measure the time, but it takes a while of many seconds. You will see. Come on, do it. Yeah, That's 50 milliamps. And if you take it away, you are back to the 5 milliamps. Then the second mode that BigClive found out is if you short the output, it will start to bring. This means that he knows that there was a short and it turns the voltage down to 18 volts. Let's test this thing with 18 volts. Does it work? Yeah, 18 volts. It is still 18 volts. And let's wait if it goes up to 50 milliamperes in this mode too. It takes quite a while, but that's the microcontroller. That's the timing of the microcontroller. Let's see if in this mode we have the switching between 20 and 50 milliamps. Doesn't look like that. It doesn't switch it. In this mode, it doesn't switch to 50 milliamps because probably it thinks this is a low power LED. But when I go back, if you short it again, now we are back to the 355 volts or something. Let's go again here, 19.4 volts. And now normally it should go after a while to the 50 milliamps again. Takes a while. No. Now we're back. Okay, this happens only in the high voltage mode. Yeah, what else do I say? Nothing happens. Anyway, let's tear this thing down and let me show you the whole schematic, and let's go through the circuit itself. Let's put that away because even if it is not very powerful, it will hurt. By the way, guys, I forgot. If you like my videos, if you like what you see, give me a thumbs up, please. Subscribe to my channel. This helps me a lot, much more than you think. I saw that many of my viewers, the majority of my viewers, are non-subscribers. Guy, it's Christmas, make me a gift. Just subscribe to my channel. It's free, costs nothing, and it helps me a lot. Okay, let's continue to the teardown of the schematic. So, and here we have the dismantled device. This is how it looked. This is the inside. Honestly, not bad at all. Very nice construction for that price range. Yeah, this, I don't know what it paid, $12, $13, 13 euros, something like that. Cheap. Very cheap. Here you have the 3-digit 7 segments. The whole thing consists of 4 parts. Let's take a look at the schematic. I completely reverse engineered the schematic, this thing, and it looks like that. If you go a little bit up here, we see the whole schematic, the 4 parts. The most easy part is the CPU itself. Yeah, there is no reverse engineering on that. It's unnecessary to do it. It's just a microcontroller with a few resistors going to the 3-digit segments, and that's it. Yeah, this is exactly this part here, what you see, this. And the microcontroller is completely blank, so there is nothing to say. It's a generic 8-bit controller, and that's it. The interesting thing is that what the controller does. First of all, it senses the output voltage and displays it. Then it senses when to switch between 19 or 18 to 300 volts. So this is something that BigClive found out. If you short the 2 output leads, after a while, this thing goes down from 300 to 19 volts. and we can see it after that in the schematic too. So it, of course, it's done through the sensing. If this thing is for longer time 0, it goes down with the output current, with the output voltage, sorry. And the next thing is, after a while, to step up between 20 and 50 milliamps. This is what the microcontroller does, nothing more, nothing less. But let's go to more interesting stuff. Here we have the first part. This thing is nothing else as an offline flyback converter. You have the rectification part here, snubber circuit. Interesting is that here is used a flyback controller, but that is more or less intended to be a constant current controller for LEDs. Anyway, they use this one, I don't know why. Yeah? Normally, this controller does not need all this feedback. The reason why they're using the feedback is to keep the 300 volts here, or whatever it is 220 multiplied by 1.41, 300 something volts, keep constant more or less through. They have a resistor divider here that if it is 300 volt, it is approximately 2.4 volt here, yeah. Then you have the TL431. This is an IC that is used in millions of power supplies. At the end, it is nothing else as a comparator. So that means it has an internal 2.5 volt reference. And if the voltage here goes over, is equal over to 2.5, it conducts. That means that the optocoupler, the LED is lighting. Here we have a 12 volt stabilization. That's the supply for the optocoupler and for the whole system. And on the secondary side, here we should have 17 volt because it has an internal 70 volt shunt regulator here. Through the primary side, rectification 300 something volt down to 17. And this goes directly to the ROVP. Normally, this should be a resistor here, yeah. But it seems that if it goes over 300 volt, then you have a voltage here, I didn't measure it, that it is enough to pull down, to rail back the PWM, so the whole thing is kept on 300 volts, yeah. This is the whole thing. It's interesting that they're using this chip. Probably either they had it, or it was cheaper than a normal offline PWM controller, flyback PWM controller. So nothing much here. The primary smoothing capacitor, then the secondary rectification here, secondary smoothing capacitor, two 1 kilovolt ultra fast diodes in series, because the spikes that generated here goes over 1000 volts, so this both of them two in series, otherwise they would die. And the transformer here, called L1, interesting, has a secondary winding that it is approximately 9 volts or something, and feeds this 3.3 volt regulator that is just for the CPU itself here, for the microcontroller. So this is more or less the flyback part. That is, the interesting of the flyback part is this IC. I will show it. I will show the more interesting active components, the data sheets, after we go through the schematic. Something else that is very interesting to say is that this device here, what you see, is really nice for Chinese standards. Other devices would not have all this part here, and we'll go directly from the primary rectification, of the mains rectification, directly to the rest of the circuit. Here it means that this thing is completely mains isolated. Well, this is the idea. How good it is isolated depends on this transformer and how good the internals of this transformer are, but at least it is completely isolated in comparison to other devices that I saw. Another thing is that you see this Y1 capacitor between secondary and primary for the common noise, a common mode noise. Yeah, normally in cheap Chinese devices you have just a normal MLCC capacitor, goes to 1 kilovolt, 2 nanotube, not a Y1 security capacitor. But this one, let me bring it. Yeah. This is a Y1 capacitor. Yeah. So to be honest, I like the construction. I like what they did. I like what they thought. You see here. Let me show you near more of that. The separation between secondary and primary is quite good. It's really good. It's the whole width of this optocoupler. Then you have phrased out, milled out the connectivity between the primary and the CPU. This could be a little bit better. Yeah, this is not really the widest distance, but okay. This is why they made a milling here and don't let it open. So let's continue to the second part. That is the first part that does the current regulation. This thing uses again a DU8613, that it is a constant current, come on, sorry, LED controller, offline. Normally this thing is connected directly to here, without this thing, but they made a decision again to make this device as safe as possible, down to a price, of course, yeah. What do we have to say here? Nothing much. Internal shunt, internal rectification through these two in series resistors, smoothing. The capacitors, most of the capacitors I didn't measure because I would have to desolder them, and I didn't do it. Anyway, then this is nothing else as an offline buck converter. Yeah, here you have the buck part. Inside you have the MOSFET, storage inductor, the outside capacitor, the smoothing capacitor is not a big one. This is the inductor, the capacitor. This is the secondary filter capacitor, is a 10 microfarad, 400 volts. Should be 105 degrees if you can trust what it says. And here you have the first interesting part of this section. You have the switching between 20 and 50 milliamps. And nothing more here. You have from the current set, CS is current set. I will show you the data sheet of this device after the description of the schematic. Normally, this is connected to a 10 ohm, I think it's a 10 ohm, can I read it? Yeah, 10 ohm resistor, that would be default 20 milliamps. And when the microcontroller, again isolated through the optocoupler, switches this MOSFET and parallels this 6.8 ohm resistor to the 10 ohm resistor, you get 50 milliamps, that's it. And here we generate the 0 point for the, this is the 0 point both for the LEDs and for the microcontroller. So the secondary of this transformer, the minus part, sits on this line, on this trail, on this rail here. After that, we go directly to the last part, that is nothing else than a soft start, voltage sensing, and the 19 or 18 to 300 volt switching. This part here is again of interest because it is a soft start. This capacitor is what it makes the curve like that to soft start. These two resistors in combination with this 12 volt Zener provides some voltage with a very low current through D9 and to the output LEDs. As long and in parallel, this 12 volt here charges with the resistor R12, 1.2 megohm, charges at 10 microfarad. This is the only capacitor I desoldered because this one is interesting to measure. This is a 10 microfarad capacitor. When the capacitor is charged to a level that triggers the gate fully of this MOSFET, then the whole current goes through. Let's say not the current, the whole voltage goes through. But then here the regulation happens, because if it sees that the load has a low resistance and draws more current, this regulates back the voltage here from this part. And the last thing is you have the sense, the output sense part of for the LEDs, that it is made with these two resistors in series. This is the lower part of the upper part of the divider. This is the lower part of the divider. Some little bit smoothing goes directly to the microcontroller input. The display is a little bit off. It's a little bit too high, I think, for the voltage that is in reality here. If somebody would like to adjust it or to make it a little bit more precise, that I couldn't care less, to be honest. Yeah, you have to adjust this resistor, make it probably, if it is a little bit too high, then you make this a little bit smaller. Probably put another resistor in parallel or remove that and put a trimmer. But where this resistor is, it will be not that easy. It's, I think, what does it say? R22. R22. And somewhere here. R22. It's easy. You can put a trimmer here. Would be possible. Yeah? Perhaps I would do it and I would try it. So then the last part is you have the switching between, let's go a little bit back, the switching between the 300 volts and the 19 volts. This is probably necessary, or they did it, if you have diodes, LEDs, that are not, I don't know, 100 in series or 50 or 10 in series, but you have single LEDs with 5 volt forward voltage, yeah? Then it doesn't make a sense to continue driving it with 500 volts. This shuts, this regulates down to 18 volts. Very easy. This is something that the controller does, the microcontroller, by sensing probably, not probably, they cannot do it differently. If you short the leads, these are the output leads, for a amount of time, the controller takes that there is too much current drawn and regulates, switches this transistor to on through this 18 volt Zener diode. So you have here only 18 volts. That's all. At the end, a very nice gadget. Honestly, I bought it just to reverse engineer it. I saw a video from at bigclivedotcom channel showing this device. I liked it, to be honest. And I thought, yeah, I want to completely reverse engineer it and play a little bit with it. I'm not into LEDs. I never made a project with LEDs, to be honest, only with LEDs just for indicators. But I will show you after that, after we finish with the schematic that we already finished, to be honest, yeah, the data sheets of the more interesting parts here. By the way, this is how it looks when this thing is put together again. There's a nice detail here that they do not use cables to connect these banana jacks, input jacks, I don't know how to call them, yeah, terminals, yeah, but they use this pin terminals here to connect directly to the banana part. I like it. No cables, easy to assemble, and more sturdy. Yep, so here we have the schematic again, just to show you the position of the parts. That I will show you the data sheets. Let's start with this one. This is this part here. It's called the high precision PSR, constant current LED driver, blah, 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 blah. Anyway, this thing is thought to be used like that. Yeah. Not too many external parts, just connect directly the LEDs, and the whole thing is regulated through the primary side. The current regulation is done through the primary side and the voltage sensing, both. But for some reason, they used this chip like a normal flyback converter with a feedback, a voltage feedback, and of course the current sensing is here with this 1 ohm resistor. But anyway, it is a nice touch. The idea was, as I said before, here you see the internals. They're using this ROVP input to regulate the output voltage or to limit the output voltage. And here you have the 17 volt shunt regulators and a regulator for the VCC through this resistor here. The whole idea is to make this thing isolated from mains through this transformer and of course the flyback converter. That's an offline flyback converter. After that, we come to the next part that in reality, as I showed before, this part here should be connected here without all this caboodle here. But this is just for isolation. And we come to this one. Of course, I didn't find any English datasheet. I have to translate it online. And it says again, high voltage, high precision LED constant current driver. This is a real current driver. In the end, it is nothing else than an offline buck converter. Here you have a reversed buck, more or less. Yeah, nothing more to say here. This is the DU8613 from a company called Duty Cycle, or whatever you called it. And it's a LED buck driver, constant current buck driver. Then the next thing is perhaps to show you this MOSFET that they use here. It is a generic N-channel MOSFET, but I found the schematic, the data sheet of it is nothing special. 20 volt 4 amps N-channel. Then we have the optocoupler. I have a data sheet, but I didn't show it here. It's a generic EL817 vulnerable HWL300. It is used everywhere in every switch mode power supply almost here. The next thing what we have here in the soft start circuit is this high voltage MOSFET. Nothing, absolutely nothing to write home for. It is 600 volts, 7 ohms RDS on, not very fantastic, at 1.4 amps at 25 degrees temperature. Nothing really special. It is in a TO252 pack, SMT, and soldered on a heat pad, on a cooling pad that is on both sides through via, connected through vias. What else do we have here? Yeah, there are a lot of high-speed diodes. For example, this one, this one, this one, this one, this one, etc. These are just SMT ultra-fast rectifiers, 1 amp at 1 kilovolt. That's it. And they are quite fast. I use them quite a lot of times. It's the ones that are higher voltage, for example, are 75 nanoseconds for RRT, reverse time recovery, and the lower voltage one is with 50. And you see here the capacity, junction capacitor, that the higher it gets, the lower the capacitance gets. So this is a standard thing that is used in switch mode power supplies. And the last thing what I want to show you is this transistor that switches between this one here. It has a reason that I draw it like that, because it is a digital transistor. 8D, the marking, is the UN2214 NPN, but a digital transistor. That means it has an voltage, it has a base resistor and a bias resistor, both. And it is 10K and 47K. Why they used another one? Probably because this is what they had and this is what they used. Who cares? There's no big difference with that, yeah? So they used it. 18 volt Zener, and the TL431, I didn't show it. So this is what I wanted to show you. That's it for now. Well, that was the video for today. I hope you liked it. Normally I don't show this kind of gadgets. This is not my métier, my part to do with LEDs and these things, but I like the design. I like how this thing is built. Yeah, and this is why I made this complete schematic here, the complete teardown and reverse engineering. Thank you again for watching. Give me 1 or 2 thumbs up. Subscribe to my channel, please. Stay safe, my friends, and see you in the next video. See you later. Cheers. Bye.